All right, this is going on page 103 when we're done. Page 102 in your ISN will be the title page that says 6 weeks. We made it. We've all survived this far. Okay, so today we're going to look at equivalent representations of trigonometric functions. So equivalent representations of trig expressions or functions. We've looked at equivalent expressions of a lot of things. But one way you can think about it is I could have 1/2 and I could have 2/4. I could also have 3/6. They all look different, but they all have the same value, right? Square root of 20 is the same thing as 2 square roots of 5. So it's similar to that, but not exactly, but just kind of give you an idea. All right, so we have what are called trigonometric identities, some of which we have to just know. The good news is everything in this chart, you already know. So tell me, what is the reciprocal of sine? Secant. Okay, so sine is 1 over cosecant x, which means that cosecant is 1 over sine x. Okay. What's the reciprocal of cosine? Secant. So cosine of x is 1 over secant x, which means secant is 1 over cosine x, or theta or alpha or whatever your argument is, but always make sure you have that argument there. Then what is the reciprocal of tangent? Cotangent. So tangent can be 1 over cotangent x, but there's another way we can look at tangent. Tangent's what over what? Sine over cosine. So then cotangent could be 1 over tangent. Or what do you think another way to look at cotangent would be? Cosine over sine. You got it. All right. Everybody good with all that? Perfect. All right, so what we can do with these is we can manipulate things so again they look different but they have the same value or they mean the same thing. So this first one says we're going to let f of x be this function. We're going to rewrite it as an expression involving tangent x and no other trigonometric functions. So there's a couple ways to go about this, but we're going to kind of baby step our way through this so that we don't get all mixed up in this. I'm going to take this fraction and I'm going to rewrite it so it's just not like one big fraction. Here's what I mean by that. We're going to write the numerator. So this is sine of x times secant squared x times 1 over cosecant x. Would you agree that that is the same thing? Now, if you fully understand fractions and you're not going to make up math, maybe you could skip that step. But if I multiplied it back together, I would get that back, right? But as it is right now, then I can see this as 3 separate things. Now, my goal is for it to be involving tangent and nothing else. And then I know tangent is either 1 over cotangent or sine over cosine. So I think the sine over cosine goal would sound better right now. And so I'm going to change all of these, if they need to be changed, into something that is either sine or cosine, which means this first one I'm going to leave alone. It's just sine of x. Then what is the reciprocal of secant? Cosine. So secant squared I can change to 1 over cosine squared. And then what is the reciprocal of cosecant? Sine. Okay, so I'm going to change 1 over cosecant to sine of x. So it's just a bunch of substitution. Everybody okay with where everything came from? So now I'm just going to multiply straight across. In the numerator, I'm going to get sine times sine, which is sine squared. In the denominator, I have cosine squared. And then sine over cosine gives me what? Tangent. So sine squared over cosine squared, tangent squared x. And we're done. What questions do you have? So let's say that x equals pi thirds. if I substituted pi thirds in here and worked it all out, got an answer, or I substituted pi thirds in here and worked it out and got an answer, or in here and worked it out and got an answer, then all three of those would be the same. Does that make sense? That's why did I do something wrong? Oh, because this is sine squared over cosine squared. And sine over cosine. So let's say instead of sine squared, I had sine over cosine times sine over cosine. Okay. Would you agree that if I multiplied those together, I'd get this right here? Okay. So then this gives me tangent, and this gives me tangent. So then when I multiply them together, I get that. Okay, does that make sense? So the reciprocals all work the same way. So if I have cosine, the reciprocal of cosine is secant, or the reciprocal of cosine squared is secant squared. All those go together. Okay, good question. So I said pi thirds. What is the tangent of pi thirds? Square root of 3. If I square the square root of 3, what do I get? 3. So it was a little easier to put it in here than to do this one, or to do the other one, or to do the other one. That makes sense? And I just made up pi thirds. It doesn't really matter. Oh, I guess I was pointing with my eraser. What questions do you have? Anything? All right. Let's try another one. Now, what we're going to do tomorrow is finish these notes, like I said at the beginning. We're going to finish these, and then I have like a little extra piece that's going to go with it, where we're going to practice a whole bunch more of these. Because what we're doing in these first two examples, it's something else that just kind of takes practice, and you need to see some more examples and how it all works. There's only 2 in this set of notes, but I felt like there should be more. So right now, as long as you can follow along with me and you can kind of make sense of what's happening, just know we're going to practice some more, and then it'll become easier and easier like everything else once we practice. All right, so now I'm going to rewrite this one. Cosecant times tangent. And I'm going to rewrite it as an expression involving secant and no other trigonometric functions. So it's telling me this because I need to know where to stop. Like here, I could have stopped here, but that didn't satisfy this, so I stopped here. And then we're going to do another one a little later on in these notes where we're going to stop where it tells us to stop, but then we're also going to go a little farther so I can show you could make it into something else as well. So I'm going to take this, and since I want secant, I know tangent gives me something over something, so I don't know how I'm going to get that directly. But what is secant the reciprocal of? Cosine. So basically, I'm trying to get cosine 1 over cosine somewhere by itself. So with these, one of the strategies, and there's a bunch of strategies to attack these, is one of them is to change everything into sine and cosine. Do you want to work every single one of them like that? Not necessarily, but that would definitely work here. So cosecant, what's that reciprocal of? Sine. So I'm going to change that to 1 over sine x times, and then tangent, I could write it as 1 over cotangent. I don't know if that's going to help me. Instead, I think I want the quotient that is sine over cosine. Okay. Then can I reduce this? I can cancel those signs out. That gives me 1 over cosine x. And the reciprocal of cosine is secant. What questions do you have? All right, so we wrote 8 identities up there. And so again, there's a reference sheet, which again I'll show you tomorrow because I didn't think to open it today, to show you all of the trigonometric identities that you could work with. And what I used to use as a reference sheet when we did identities and stuff. You do not get one of those on the AP exam. But the good news is you don't have to know as many as what's on that reference sheet anyway, and I'm going to give you a way to know how to get to what you need. But again, you have to practice and you can't just ignore it. So yeah, you have to know those up there. You already know it. And then we're going to come up with one here that you absolutely have to know, but I'm also going to show you where it comes from. And then once we know that one, that's going to lead us to some others, okay, how to discover them if you need to do it over and over again. So we are going to discover several interesting properties and identities, and we're using our unit circle. So here, we know it's a unit circle because the radius is 1. This is our x value, this is our y value. All that should make sense to you, right? One of the first things you learn how to do with right triangles is find a missing side. like in 6th grade. And what do you use to do that with? What's it called? Pythagorean theorem. So if I set up Pythagorean theorem, because this is a little right triangle right here, I could say that y squared plus x squared equals 1. Y'all agree with that from that little triangle? That's what's happening there. All right, so any point xy can also be used, or also be written as cosine theta sine theta when we have a unit circle, which is what we have. And then we know, and we've known this for a while, x equals cosine theta and y equals sine theta. Since that is true, if I substitute these in right here, then I would get sine squared theta plus cosine squared theta equals 1. You see where that comes from? It comes from the Pythagorean theorem. Instead of x and y, I put in the sine and cosine that we already knew existed. And this is called the Pythagorean identity. This one you have to know. If you know this one, it can lead us to a couple other things, all right? Sine squared plus cosine squared equals 1. We good on that? Okay. Flip this over. So let's start with this. We're going to start by writing sine squared theta plus cosine squared theta equals 1. And then we're going to box this because we're going to box the ones that, like, this is what we're getting towards. But not only is this true, but because we know this isn't going to give us a different one. We're just going to rearrange this. Let's say just how we substituted something in for tangent just a minute ago. If I needed to substitute something in for sine squared, I know from this that I can say that sine squared theta equals 1 minus cosine squared theta. Would you agree with that? Or, let's say I needed to solve for cosine squared theta. Cosine squared theta, that would equal 1 minus sine squared theta. So obviously I want them written on your notes, but you wouldn't necessarily have to write all of these out every time because you could look up here hopefully and figure out how that works. But that's how we might be substituting them in sometimes, or we might be substituting it in for 1 or whatever, but you can rearrange them. All right, we good with that? Okay, so then let's, in this next little column here, we're going to rewrite again sine squared theta plus cosine squared theta equals 1. And then we're going to divide each term by sine squared theta. Then after we do that, we're going to reduce. What do you think sine squared over sine squared gives me? 1. So this is 1 plus, and then what is cosine squared over sine squared? Cotangent, I heard it whispered over here. Cotangent squared theta. And then what is 1 over sine? Cosecant squared theta. So this is a second Pythagorean identity. If you don't remember it off the top of your head, that's okay, because you can take this one and divide everything by sine, and you've created it and have everything in the right spot. Does that make sense to you? Just a very simple simplification there. And just like over here, I could say, well, 1 is equal to cosecant theta minus cotangent theta, or cotangent squared theta, or that cotangent squared theta is equal to cosecant squared theta minus 1. But it all comes from this. Okay. That's why if you know where it comes from and how to develop it, you don't have to have a sheet of stuff memorized in your, in your brain, just stuck in there. You can create it along the way. Okay? We all okay with that? All right, so we're going to do it again. Sine squared theta plus cosine squared theta equals 1. This time we're going to divide everything by cosine squared. And then I'm going to give you a second, and I want you to see if you can simplify that. All right. What do you think? Is that what you got? See how that works? All right, so then we're going to box this one. Then we're going to come up with, we could say that tangent squared theta equals secant squared theta minus 1, or that 1 equals secant squared theta minus tangent squared theta. Notice how your basic math, your basic arithmetic, your basic algebra skills, they don't change. We're not making up math. We're not making it any harder because it's trig. Same thing that we do on everything. Everybody good at this point? Okay, so we wrote a whole bunch of stuff up here, right, and found a whole bunch of things. So I just want to make sure that you know, like, what your 3 goals are. And again, the first one that you absolutely have to know is sine squared theta plus cosine squared theta equals 1. Okay. Now, if you also know the other ones, because you can kind of see a pattern and you have a way of remembering it, totally fine. If not, you know how to get them from here, and that would be 1 plus cotangent squared theta equals cosecant squared theta, and then tangent squared theta plus 1 equals secant squared theta. And if you notice on the second 2, both of them have a 1 on the left-hand side, but one's at the beginning, one's in the second one. It really doesn't matter what order it's in. It's just usually written like that on formula sheets because of where it came from, because that's just kind of how it falls. But it, you know, you can remember it however you need to. All right, what questions you got? Okay. So this next identity might seem a little funky, and it's one, even all the years I've taught pre-cal, we've done identities. We've never really looked at this one. I don't know why we haven't, but there's probably a really good reason we need it. But I wouldn't stress out too much. Like, I'm not just going to skip teaching you something, but I feel like if this next one, because I know you're not going to like it as we start writing stuff out, if it showed up, it might be one multiple choice question. So if you could get it right, great. If not, it's not going to kill you, okay? That's the way you kind of want to look at some things. Like, is it really worth my time and stress to figure out this when I could just kind of move on and worry about the rest of the stuff? That's kind of how I feel about this one, but that's just really my opinion there. Okay, so we have, again, unit circle, right triangle. This is 1, this is x. Instead of saying that this is y, which it totally is, we're going to call it h for the height of the triangle. Okay. Then we are going to do Pythagorean theorem again. H squared plus x squared equals 1. And then I want to solve for h. So that means that h squared is equal to 1 minus x squared. So h is equal to the square root of 1 minus x squared. And it's not plus or minus, it's only positive because it's a height, which is a length. So that's also why we called it h and not y, because it's just going to come out positive every time, and then you would need to know what quadrant you're in if you needed to do that. Okay, so with that said, everybody okay with how we got h? That's why this triangle over here is labeled like it is. This is your x value, this is your height, which is technically your y value, so your ordered pair here is x, and then square root of 1 minus x squared. Is this a unit circle? Yes, and how do you know? The radius is 1, okay? It's a unit circle. So since it's a unit circle, that means this is my cosine value, this is my sine value. Make sense? Like, that's always true. Cosine, sine. So when we get down here, with this triangle, we can see that cosine theta is equal to x, right? Because it's my x value. Therefore, if I want theta, I take the cosine inverse, and it's equal to the cosine inverse of x. Right? Sine theta is my y value. It's equal to the square root of 1 minus x squared. Therefore, if I want theta, theta is equal to, when I take the sine inverse of both sides, the sine inverse of the square root of 1 minus x squared. Everybody understand where everything came from? And again, if you needed this, you can create all of this just from a simple right triangle, just like we did, okay? And then here, because this is theta, this is the x and y that we used here. So theta, it's the same angle for both of these. Since we're talking about the exact same angle, that means that this has to equal this. So the cosine inverse of x has to equal the sine inverse of the square root of 1 minus x squared. If I redid this again and then labeled the height as x and, turn my triangle or whatever, then this is going to equal the cosine inverse of the square root of 1 minus x squared. So you can write it in either direction. So let's write them in here. We've got cosine inverse of x is equal to the sine inverse of the square root of 1 minus x squared, which means the sine of x equals the arc sine, the square root of 1 minus x squared. Because remember, arc sine, same as the inverses, right? And then, let's write these over here. So sine inverse of x is equal to the cosine inverse of the square root of 1 minus x squared. And similarly, arc sine of x equals arc cosine of the square root of 1 minus x squared. You've seen it. I'm going to do a little bit with it. We're not going to stress out about it, okay? The other identities, you're going to need to understand much more, and it really won't be that big of a deal once we practice them, I promise. All right, let me give you part 2, which I forgot to put continued at the top, because I do that a lot. So this is also going to go on page 103 when we're done. So we have another one of these where we're going to rewrite it. We're going to use our identities. So they've given me this function. I want to rewrite it as a fraction involving powers of cosine and no other trigonometric functions. So I have a fraction. Let's work with the numerator. Numerator is tangent. How else can I write tangent? Sine over cosine. Good. So sine of x over cosine x. And then cosecant's in the denominator. How else can I write cosecant? 1 over what? Sine. Now, I have a fraction and a fraction. No big deal, right? I can just use my keep, change, flip, and not make up math. So I'm going to keep the numerator, sine of x over cosine x, change division to multiplication, and multiply by the reciprocal, like so. So when I multiply straight across now, this will give me sine squared x over cosine x. So this is an equivalent form of this, but it's not only in powers of cosine. Okay? So let's think about what that might look like for us. Without looking at anything, what is the Pythagorean identity that we have to know? How does it start? Sine squared theta plus what? Cosine squared theta. What does that equal? 1. Okay, y'all agree with that? See, we've already learned 1. Now, I would like to replace this sine squared. From this, looking at that, what can I replace sine squared with? What would sine squared equal if I solved that? 1 minus cosine, right? If I solve for sine squared and subtract that over there, sine squared is equal to 1 minus cosine squared, right? You can write it out if you need to, but you don't have to if you think about what's going on up there. So that means that this can be 1 minus cosine squared over cosine. So now I have this written as a fraction involving powers of cosine and no other trig functions. We are going to box this because this is what they asked us to do. But then we're going to take it a little farther because I want you to see that we could make another equivalent form, right? Which some might say would be better. Kind of depends on what your goal is, which our goal right now is to just answer whatever they said, but we're going to stretch this out a little bit. I can separate this fraction, meaning I can make this in, oh, and look at what I did. Here, I did a big fat no-no. I left off x on the bottom. You have to have an argument. Some x, okay. So I can make this 1 over cosine x minus cosine squared x over cosine x. You see how I split the fraction? Because if I put it back together, I would get this back, right? Everybody okay with that? This is one way you can split a fraction. Now I'm going to simplify. How can I rewrite 1 over cosine? Secant. Okay. And then minus, what do you think is going to happen here? Anything going to cancel out? Yeah, this will cancel out with one of those in the numerator, so that just leaves me with cosine x. So this is another equivalent form without any fractions in it. But again, depending on what you want it for, you know, you can even do different things, I guess. What questions you got? We all good? Okay. And this is going to come with more practice. We're going to look at a ton more examples and stuff tomorrow. But before we get there, we are going to look at another identity. So this is another identity that you have to know, okay? And once this is all written out, this is going to look like crazy nonsense. But I promise you, if you look at it, you think about what the patterns are, it's not going to be that big of a deal. We're going to look at what's called a sum identity. So I'm going to have the sign of alpha plus beta. Okay, so it's like sine of pi halves plus pi thirds, whatever the two angles are. I don't know, alpha, beta. So we start off with sine of the first one, so sine of alpha, times cosine of the second one, so cosine beta. Okay, so the trig expressions alternate. Then since this is addition, I have addition here. And then I alternate the other way, and I do cosine of alpha, sine of beta. See how that works? Cosine of the first one sine of the first one times cosine of the second one plus cosine of the first one times sine of the second one, right? The trig expressions alternate. The signs do not. They're the same, okay? You commit this one to memory, you'll be able to use the pattern to figure out everything else we're about to do. So the other thing, one of the things we can get from this is to know how it's related to cosine. Cosine of alpha plus beta. So this started off, this was sine of alpha plus beta. We started off with sine of alpha. So this one starts off with cosine of alpha. However, cosine doesn't like to alternate. So I get cosine of alpha times cosine of beta. Now here, let me say it again. The trig expressions alternated, so the sign stayed the same. If the trig expressions don't alternate, then the sign changes, and this is minus. And then we have sine of alpha times sine of beta. Okay. So do you see the patterns there? When the trig expressions alternate, the signs do not. When the trig expressions stay the same in each term, then the signs change. You okay with that? And again, I mean, it might not be like today you're like, oh, I can rattle these off, but you have to look at this stuff and look for the patterns, and it's not going to be that big of a deal. So, I mean, you can look at it as you just have to know this one, or maybe you need to know both of them in order for your brain to make it all work out, whatever works for you. But then from this, it says using these two identities, we can also derive identities for the subtraction, or the difference identities, and what we call the double angle identities. So my sign, if I want the sign of alpha minus beta, then the rest of this looks the same except the sign changes. So these two pieces stay exactly the same. That's going to be the sine of alpha times the cosine of beta. And then since the expressions alternated, the sign does not, so that's minus. And then we have cosine of alpha times the sine of beta. Okay, everybody okay with that? So then if I do cosine, the difference identity for cosine, that's cosine of alpha minus beta. And again, these two pieces stay the same. So this is cosine alpha times cosine beta. The trig identities were the same, which means the sign changes. And then I get sine alpha, sine beta. So again, I know that looks like a bunch of nonsense right now, but look at the patterns so that you're able to write that stuff out for yourself. Okay? What questions do you have at this point? You don't even know what to ask at this point, and that's okay, right? Because we're gonna finish up what we can today. We're not done yet. You're gonna have a video to watch tomorrow. Don't let it overwhelm you. I probably wouldn't do it in this order if I was gonna be here tomorrow. We'd probably practice some and then go down that road. But then on Friday, I'll take any questions you have. We can go back over things, whatever. But this is another thing that takes a little time to kind of work out in your mind. All right, so that's the sum and difference. Now let's use this to come up with our double angle identities. So sine of 2 alpha, that could be sine of 2 theta, sine of 2 beta, 2x, whatever. But I'm going to write it as sine of alpha plus alpha. Would you agree that alpha plus alpha is 2 alpha? Okay, so there's a reason I'm starting it off that way. Because I'm going to take this and I'm going to use my sum identity that I have. Instead of these being different, they're both going to be alpha. So that means here this is going to give me sine of alpha times the cosine of alpha plus cosine of alpha times the sine of alpha. Do you see how I just substituted that in? Oops. Everybody with me at this point? And understand where all I did was plug in alpha to both of the angles right here. Now I'm going to simplify this. So sine of, like we said, 2 alpha, or again, 2 theta, 2x, whatever. Then when I look at this, I have sine times cosine, cosine times sine. Are those technically the same thing because they have the same angle? Yes. It's like 2 times 3 and 3 times 2, right? So really I just have 2 of the same thing. I have 2 sine alpha, cosine alpha. And that is your double angle identity. And if you don't just remember what it is, you can get it by using this one right here. That's why this one is a must. You get this one, it can lead you to other things, or maybe after a little bit of practice, you just kind of know some of them. That's good too, but if your brain doesn't work that way, I don't want you freaking out or worrying about memorizing. Memorizing doesn't always go so well sometimes. All right, so let's look at cosine for our double angle. Let's do cosine of alpha plus alpha. So again, I'm coming up here. So this is going to give me cosine of alpha times cosine of alpha minus sine of alpha times sine of alpha. Just substituted it in. Everybody okay with where all that came from? Okay, so now we're going to simplify here. This is going to give me cosine of 2 alpha equals, now cosine times cosine is cosine squared because it's the same angle. I couldn't do that if it wasn't the same angle. Minus sine alpha times sine alpha is going to be sine squared alpha. So that is your double angle identity for cosine. But then we also have other versions of it. And really, if you had a formula chart or a reference sheet, all three sometimes show up. So we're going to say, or, let's do some substituting. Instead of cosine, for cosine, can't I substitute in 1 minus sine squared? So I'm going to substitute in 1 minus sine squared alpha, and then subtract sine squared alpha. So that also would give me then 1 minus 2 sine squared alpha. Not saying you need to remember all of these, but if you needed to manipulate it, you could manipulate it into that. And then we have another one. Or, instead of that, let's substitute in something for sine squared. So cosine squared alpha equals, not equals, oh my goodness, minus, and instead of sine squared, I'm going to do 1 minus cosine squared. And then when I simplify that, that would give me 2 cosine squared alpha minus 1. Just substituting and simplifying. Okay. So then for what we're going to substitute in, or not substitute in, write out in here, my double angle, that was sine of 2 alpha. That was just 2 sine alpha cosine alpha. Right? And although we did some more, we did a few for cosine, really the one that kind of your original goal is cosine squared alpha minus sine squared alpha. It's not the Pythagorean identity because we're not adding. Okay? And then I'm going to let you copy these from the top, but here's what I want you to write in. I want you to do the sine of alpha plus beta and the sine of alpha minus beta. That's why those are called the sum and difference identities. And then here, cosine of alpha plus beta and cosine of alpha minus beta. Okay. Y'all go ahead and fill those in. While you're doing that, I'm going to give you your assignment just so it's one less thing for the substitute to handle tomorrow. But remember, when you come in, you will have something else to pick up because I will start the video here with example 4. We're going to work through the rest of this, and then we're just going to work through more examples of simplifying some identities.